Your Spark job ran in 8 minutes yesterday. Today, the same job, the same cluster, the same data took 22 minutes. Nothing changed, or did it? If you've ever stared at a Spark UI wondering what went wrong, this video is for you. Today we're going deep into 3 concepts that most engineers learned too late: spilling, tungsten, and whole-stage code generation. These are not just theory. They are the actual reason why Spark jobs speed up or silently fall apart. And by the end of this video, you won't just know that Spark is fast. You'll understand exactly why, and you'll be able to explain it in any interview. In the previous video, we explored how Spark manages memory internally, execution memory, storage memory, and how unified memory balances between them. If you haven't watched that yet, I'll link it in the description. But today we go one level deeper. Let's begin. Let me ask you something. Picture this: same cluster, same code, same data size, yet the job takes twice as long today. Something changed beneath the surface. Today, we uncover exactly what. Why does Shuffle suddenly become expensive? Why does Spark write data to disk? And what actually made modern Spark dramatically faster than older versions? These questions all lead to the same place: Spark's execution engine. And today we're going to explore it. Memory is a limited resource in every Spark executor. And the moment Spark starts running out of execution memory, a completely different behavior begins. Spark starts moving temporary data out of memory. This process is called spilling. And understanding spilling is the first step toward understanding Spark performance. So what exactly is spilling? Imagine Spark is processing a huge amount of intermediate data: joins, aggregations, sort operations. Everything is running in memory, but eventually memory becomes insufficient, and Spark has to make a decision: fail the application or temporarily use disk. Spark picks resilience over speed. In simple terms, spilling happens when Spark moves intermediate execution data from memory to disk because available execution memory is no longer sufficient. And this behavior is far more common than many engineers realize. Now that we understand what spilling is, the next question is obvious. Why does spilling happen in the first place? There are several common reasons. Sometimes the data set is simply larger than available execution memory. Sometimes heavy shuffle operations create massive amounts of intermediate data. And remember, during a shuffle, Spark redistributes data across executors, which means large temporary data structures need to be created. Spilling can also happen when too many tasks are running simultaneously, or when executor memory is not configured appropriately for the workload. So, as memory pressure starts increasing, Spark reaches an important decision point. The trade-off is clear: crash the VM or slow it down and keep it running. Spark almost always chooses the latter. Spark temporarily uses disk to keep the workload alive. That is spilling in action, and it's more common than most engineers realize. And here's something important. Spilling is not necessarily a sign that Spark is broken. In many situations, it's actually Spark protecting the application. Because without spilling, the executor could run completely out of memory, and the entire job might fail. So Spark accepts slower performance in exchange for keeping the workload running. And in large-scale distributed systems, that's usually the better choice. So spilling is both a symptom of memory pressure and a safety mechanism that helps Spark avoid failure. But that creates another question. If spilling helps keep jobs alive, why do engineers worry about it so much? That's exactly what we'll look at next. Let's make this intuitive. Imagine you're working at a desk. As long as the desk has enough space, you work efficiently, but eventually the desk becomes full. So you start placing documents on the floor. Now every few seconds, you bend down, pick something up, and continue working. The work still gets done, but it becomes slower. That's exactly what Spark is doing. Memory is the desk. Disk is the floor. And spilling is the extra effort required to keep working. Now here's the important question, and stay with me on this. If spilling is just Spark being smart and protecting the job, why do senior engineers treat it as a red flag? Why do companies invest thousands of dollars in cluster memory just to avoid it? The answer comes down to one thing: speed. So if spilling keeps the application alive, the answer is simple. Disk is orders of magnitude slower than memory. Memory operations happen extremely quickly. Disk operations are much more expensive. So every time Spark writes spill files and later reads them back, additional overhead is introduced. This is one of the biggest reasons shuffle-heavy workloads become slow. And it's also one of the first things experienced Spark engineers investigate. So how do we recognize memory pressure? Fortunately, Spark leaves clues. You may see high spill metrics, frequent garbage collection, increased disk I/O, slow executors, or stages taking much longer than expected. When several of these symptoms appear together, it's often a strong indicator that memory has become a bottleneck. Here's something that might surprise you. Even after engineers improved memory management in Spark, jobs were still slower than they should have been. Why so? Because the bottleneck had shifted. It was no longer just about memory. It was about the JVM itself. Think about this. Every time Spark processes a row of data inside the JVM, that row becomes a Java object. And every Java object carries hidden weight. A header, metadata, references. Now multiply that by 100 million rows. Suddenly you're not just storing data. You're storing 100 million tiny packages of overhead. And the JVM has to track, manage, and garbage collect all of them. While it's doing that, it is not processing your data. That's CPU time wasted on housekeeping. Spark engineers realized we need a completely different approach. And that's where Tungsten was born. Tungsten was Spark's internal performance revolution. Introduced in Spark 1.4 and matured through Spark 2.x, it tackled three specific problems: how data is stored in memory, how memory is managed, and how the CPU processes that data. The result was dramatic. Spark 2.x was significantly faster than Spark 1.x, and Tungsten is one of the biggest reasons why. Let's walk through each pillar. But before we explore what Tungsten does, we need to understand the exact problem it was solving. And this slide shows it perfectly. Before Tungsten, Spark heavily relied on normal Java objects. Now, why is that a problem? Every single Java object carries hidden weight: an object header, type information, references. For a single record, that overhead is tiny. But think about a real Spark job. You're not processing one record. You're processing millions, sometimes hundreds of millions. Suddenly you have millions of Java objects in memory, each one carrying its own overhead. This creates three cascading problems. First, high memory usage. You're using far more memory than your actual data requires. Second, garbage collection pressure. The JVM now has to track, scan, and clean up all those objects. And while the garbage collector is running, everything else pauses. Third, CPU time wasted. Instead of processing your data, the CPU is spending valuable cycles on memory management. So the chain looks like this. Many Java objects to high GC overhead to slower execution. This became a major bottleneck in large-scale Spark workloads. And this is exactly why Spark engineers built Tungsten, to eliminate these overheads entirely. So now that we understand the problem clearly, let's see how Tungsten solves it, starting with binary processing. Pillar 1, binary processing. Instead of wrapping every row in a JVM object, Tungsten stores data in raw binary format, directly in memory. Think of it like this. A JVM object is like shipping a book in a giant box full of bubble wrap. Binary format is the book itself. No box, no padding, just the content. Less space, faster to move, easier for the CPU to read. This single change dramatically reduced memory usage and garbage collection. Pillar 2, off-heap memory. Normally, Spark stores data inside the JVM heap. The JVM heap is convenient, but it comes with a cost. The garbage collector periodically scans and cleans it. And when GC kicks in during a large job, everything pauses. Off-heap memory solves this by letting Spark allocate memory outside the JVM heap entirely. Spark manages it directly. No garbage collector involved. Less pausing, more processing. Pillar 3, cache-aware computation. Modern CPUs have a small but extremely fast layer called the L1/L2 cache. When data fits in this cache, the CPU processes it at incredible speed. When data is scattered across memory, the CPU constantly has to fetch it from farther away. This is called a cache miss, and it's surprisingly expensive at scale. Tungsten organizes data in compact sequential layouts, so the CPU can load and process it without constantly hunting around in memory. Small change, enormous gain at billions of records. So to put it simply, before Tungsten, Spark was powerful but fighting against the JVM. After Tungsten, Spark works with memory and CPU like a high-performance engine. Binary processing cut object overhead. Off-heap memory removed GC pauses. Cache-aware layouts kept the CPU fed with data. Together, these three pillars are why modern Spark can process billions of records, in a fraction of the time older versions could. And now that you understand Tungsten, there's one more layer Spark optimized, and it might be the most clever one: the execution code itself. But even after all these improvements, one major source of overhead still existed: the execution process itself. Function calls, operator boundaries, JVM execution overhead. So Spark engineers optimized one more layer: the execution code. This optimization is called whole-stage code generation, or simply Codegen. Instead of executing many operators separately, Spark combines multiple operators into a single execution pipeline and dynamically generates optimized JVM bytecode. The result? Fewer intermediate objects, better CPU utilization, and significantly higher throughput. And that distinction is what makes Spark SQL dramatically faster than older engines. Think of a factory. Without optimization, every worker performs one task and passes it to the next, again and again. Each handoff introduces delay. But imagine one optimized assembly line. Everything flows continuously. Less handoff, less waiting, faster output. That's exactly what whole-stage Codegen achieves. Let's be concrete about why Codegen matters at scale. A single filter, projection, or aggregation carries tiny overhead individually. But Spark processes millions, sometimes billions, of records. At that scale, small overhead compounds into a serious performance bottleneck. Think about what happens during a normal execution pipeline. A filter runs, then a projection, then an aggregation, then another transformation. Each operator introduces overhead, intermediate objects, extra CPU work. Individually, these costs look tiny, but Spark processes millions, sometimes billions of records. And at that scale, small overhead becomes a big problem. This is exactly what whole-stage Codegen solves. Instead of executing operators one by one, Spark fuses them together. It generates highly optimized JVM bytecode and executes them as a single efficient pipeline. The CPU performs less housekeeping and spends more time processing actual data. This is one of the major reasons Spark SQL became dramatically faster than the traditional data processing engines. Now let's connect everything. Spark starts in memory. When memory pressure increases, spilling protects the application. Tungsten reduces memory overhead. So Spark performance isn't powered by one feature. It's powered by multiple optimizations working together. Now let's move from theory to reality, because everything we've discussed so far doesn't happen in isolation. It all happens during a real Spark job. So let's walk through what Spark is actually doing behind the scenes. Imagine you're processing hundreds of gigabytes of data. Spark begins by reading data from a source. It could be files, a database, or a streaming platform like Kafka. Next, transformations begin. Filters. And this is where things get interesting. As intermediate data starts growing, execution memory begins to fill up. At first, Spark tries to keep everything in memory, because memory is the fastest place to process data. But if memory pressure becomes too high, Spark starts spilling some intermediate data to disk. Not because something went wrong, but because Spark is protecting the job from failure. At the same time, Tungsten is working behind the scenes, using compact binary formats, reducing object overhead, and minimizing garbage collection. So Spark can process more data using less memory. And while all of that is happening, whole-stage code generation is optimizing execution itself. Instead of running many separate operators, Spark combines them into efficient execution pipelines and generates optimized JVM bytecode, reducing unnecessary overhead and keeping the CPU focused on actual data processing. So when you run a Spark job, you're not just running transformations. You're running an entire optimization engine. Spilling is predicting the workload. Tungsten is optimizing memory. Codegen is optimizing execution. And all of these components are working together continuously to process massive amounts of data as efficiently as possible. In interviews, most candidates stop at, Spark is fast because it uses memory. That's incomplete. A strong answer covers the full optimization stack. Spark combines memory management, binary processing, off-heap memory, and whole-stage Codegen. Together, these optimizations deliver high performance. Let's land this. Every Spark job you run is quietly powered by three things we covered today. Spilling, which keeps your job alive when memory runs out. Tungsten, which makes every byte of memory in every CPU cycle count. And whole-stage Codegen, which makes the execution itself blazing fast. These aren't just exam topics. If you're debugging a slow Spark job at work, these are the first three places you look. Check your spill metrics in the Spark UI. Check your shuffle RAID/write sizes. And look at your physical execution plan. Does it show whole-stage Codegen? If it doesn't, something is blocking the optimization. The engineers who understand this level of Spark internals are the ones who get promoted, who debug the hard problems, and who confidently walk into any data engineering interview. That's where you're headed. In the next video, we go even deeper into the Catalyst Optimizer, the component that reads your SQL query and silently rewrites it to be faster. It's one of the most underrated features in Spark, and most engineers have no idea how it works. I'll see you there.